Hello, physics students. This is Mr. Kraft coming to you from my house. You should by now have received the packet that I uploaded. It's going to be the one that deals with electricity with charge. That's the topic we're going to be talking about next. And I want to just unpack some of the concepts that the packet talks about. And the most fundamental one when dealing with electricity is charge. And charge is kind of hard to define, actually, but we all know what it is. It is a quality that particles have on them that can be either negative or positive, and that when you bring them close to each other, they produce a force. So you take the simplest atom, which is the hydrogen atom, not a great drawing, but that's okay. The particle in the middle is a proton, and it has a positive charge. The particle that we say orbits it, that's not quite exactly true, but close enough, called an electron, and it is a negative sign. A very interesting thing about the word electron, you notice on the first couple pages of your packet, it shows rubbing a glass rod against a piece of silk or fur, and it produces a static charge. I don't know if you've ever done that in previous science classes or at home or whatever. If you brush a comb through your hair and tear up little pieces of paper and hold the comb by it, it will pick up the pieces of paper. That's an example of static electricity. And amber is a brownish, yellowish substance that is fossilized tree sap, basically, and it's used as a gemstone. Since ancient times, people have noticed that if you rub amber against fur or what have you, it will have much the same effect. It will produce a static charge. It will make hair rise up. It will do things like that. Well, the word in Greek, electra, means amber. And that's where the word electron and from it electricity, all those things came from. So just a little piece of information there for those who are interested in that. So clear the board. Charge is either negative or positive, and like charges, repel, unlike charges, attract. So plus go flying away from each other. Same way with minus. Plus or a minus, though, will be attracted to each other. And you've all experienced this in a slightly different version with magnets. Magnetism and electricity are different forms of the same thing. If you put magnets a certain way, they attract. If you put them a certain way, they repel. Same basic idea here. So that is why the electron, which is negative, is attracted to the proton, which is positive, and circles around it. Doesn't exactly circle around it, it forms an electron cloud, but the basic idea is that they are attracted, and that's what's going on. So let me clear canvas again. What I wanted to draw your attention to is page 473. I'm not going to write this part on the board because you have it already. It says, the principle of conservation of charge. The net electric charge in an isolated system remains constant. So if you have an object and it has a certain charge on it, positive or negative, and its net charge what you have to look at. So, for example, here, schematically, you've got 1, 2, 3, 4, 5, 6 units of positive charge and only 4 units of negative charge. So its net charge is positive 2. A net charge could be 0. That doesn't mean there's no charge there. It means there's no net charge. So if you had another object over here that had 1, 2, 3, 4, 5, 6, 7 positives, 1, 2, 3, 4, 5, 6, 7 negatives, you would have a positive 7 and a negative 7, so the net charge would be 0. So everything's going to have a net charge, 0 or positive something or negative something. And that's not going to change if it's relatively isolated. Now, if this object here were brought over close to that object or in contact with it, electrons, which is what signifies the negative symbols there, might flow over onto it, change it. But what we're talking about in this context, conservation of charge, is that the net charge is going to remain unaffected for a relatively isolated object. All right. So what I want to draw your attention to, the last thing, is Coulomb's law. And in order to discuss that, I have to go back to Newton's laws. Well, not one of Newton's laws, the first three, but Newton's equation of gravitation. You will recall, for gravitation, you have two objects, such as the Earth and the Moon. Each of those objects has a mass, which we symbolize M1, M2. And there's a certain distance between them. We measure the distance center to center, and that is D, or sometimes they use R for radius. And then you have the force between them, which in this context is basically what we call weight. And then you have capital G, which is the universal gravitational constant. And the constant is derived through experimentation. We've discussed it before. I'm not going to pull out the exact figure for it. The main thing I'm looking at is more conceptual. F equals G M1 M2 over R squared. That is Newton's law of universal gravitation. Universal because it applies to every object in the entire universe. F equals the force. So M1 times M2, those are in the top. That means the bigger the mass, the bigger the force. This is what we call a direct proportion, which I believe we've talked about in math, but we may review the concept a little bit later. Direct proportion to the masses. The radius squared, the distance between them, is in the bottom, which is what we call an inverse proportion to R squared. So in other words, the bigger the mass, the bigger the force, the less the mass, the less the force. That's what a direct proportion is. The greater the distance, the less the force. That's what an inverse relationship means. So force equals Gm1 M2 over R2. R squared, rather. I want to do some erasing here because I want you to see. I want to leave this up because Coulomb's law, which is what we're going to talk about next, is strikingly similar. Coulomb, Coulomb, Charles Coulomb, as you might guess, was French, and he was involved in a lot of the early research into electricity, electrical phenomena. And as is often the case with long deceased scientists, he got a unit of measurement named after him. Almost got it. The eraser function on this thing is very laggy. I don't know why. Okay. So Coulomb, Coulomb, and it's a total piece of trivia. The name means dove in French. It is a version of the name Colon in Spanish, or what we call in English Columbus. But anyway, Coulomb is the measure of electrical charge, as you'll see over on page 475. And it's based on the charge of an electron. Lowercase e is 1.60 times 10 to the negative 19th power coulombs, capital C for Coulomb. So if you had 1.6 times 10 to the positive 19th power electrons, that would be 1 Coulomb of charge. But I'm not too worried about that at this moment. What I'm interested in is Coulomb's law. By the way, charge, the symbol we use for charge in physics, is a capital Q, which I think is for quantity. So Coulomb's law, we said a few minutes ago that if you had two electrons or electron and a proton, what have you, two charged particles, two charged things next to each other, there's a force between them. There's a force of repulsion if they're like charges. There's a force of attraction if they're unlike charges. How much is that force? Coulomb's law, Coulomb apostrophe S, law, says force equals K, lowercase k, QA, which is the first charge, QB, which is the second charge, all over R squared. And I hope that immediately you see the similarity with the universal law of gravitation. Not only the similarity, but in fact exactly the same thing, except for the specific variables we use. So QA and QB are the two charges. Obviously, the forces between two charged things are going to be greater for a stronger charge and lesser for a smaller charge. The distance between them, inverse square law again, which is what we call that. I'll discuss that in detail in future videos. The farther apart they are, the lower the force between them. And there is a constant, which I'm not going to go to in detail about right now. So basically, universal gravitation, Gm1m2 over r squared, and Coulomb's law, KQAQB over r squared, are set up the exact same way. So the behavior of the force of attraction or repulsion between two charged objects is exactly, mathematically anyway, exactly the same as the behavior of gravitational force between two objects. And the only difference is that the units are different. QA and QB are measured in coulombs. M1 and M2 are measured in kilos. Constants are different. The radii are measured in the same units, M. So it's interesting that so many of these things work so similarly, even though they describe phenomena that are very different. Electricity, charge is very different from gravitation. And in fact, gravity is the weaker of the two forces. Electricity charge is far stronger than gravity. Simple example would be, once again, the example I gave. You brush your hair with a comb when you pick up pieces of paper with it. As tiny as the comb is, it is pulling that paper up against the pull of gravity. So a comb that you comb your hair with is stronger than the gravity of the entire planet when you pick up pieces of paper with it, which is pretty amazing. A maglev train, magnetism, as you'll learn later, is a different form of electricity or a different manifestation of it. Magnetism will lift a train up off the ground so it can go along without touching anything. That's another example of how electromagnetic phenomena are much, much, much stronger than gravitational phenomena. Okay, I'm going to close it at that. No written assignments yet. I just hope this video has been helpful in clarifying some of the stuff in the packet, and I will talk to you soon in the near future. Goodbye.